Hello everyone, welcome to SETA channel. The footage shows a 200 full ball endurance test, using my own balls. This is mainly to verify reproducibility. After several years of hard work, I finally completed it. The content of this video is an explanation of this machine and verification of its accuracy and reproducibility. The purpose of creating this machine is to verify billiards. It will be used to verify tools and phenomena. As for equipment, this includes the performance of cues, tips, chalk, balls, cloth, cushions, and so on. As for phenomena, this includes practical deflection values, throw, draw shots, follow shots, shooting, position, and changes in conditions, etc. To achieve the purpose, the design conditions include absolute reproducibility and precise aiming accuracy, compared to humans. And versatility that helps with various verifications. Cue point adjustment, cue angle adjustment, variable cue speed, acceleration, stroke amount, and the ability to change cues, etc. While continuing the 200 full ball endurance test, I will move on to explaining the components that make up the main unit. The idea started from a 3D printer video. A major 3D printer manufacturer was using hundreds of 3D printers to print its own parts. I became a little interested and looked into it, and found many videos of people making 3D printers as DIY projects, with parts being sold at reasonable prices. I felt that I could make a machine to accurately stroke the cue myself if I applied these principles. Therefore, the structure and parts are similar to those of a 3D printer. Of course, I also use parts printed by a 3D printer. For the basic frame, I use an aluminum frame. Since you can purchase them with specified lengths, no processing is required. I use special fittings to connect the frames together. There are various types depending on the use. For the power source, I use a stepper motor. For motor control, I use an Arduino microcontroller board. A motor driver is also essential for the stepper motor. Instructions go from the PC, Arduino, motor driver, stepper motor in this order. To convert the motor's rotational movement into linear movement, I use pulleys and belts, or AT8 shaft. As a linear motion mechanism, I use linear rails. With built-in bearings, it moves precisely along the rail. This is a simplified program screen for explanation. The feature of the stepper motor is that it can control the amount and speed of rotation precisely. It is controlled with three parameters: distance, speed, and acceleration. So, these three lines are all you need to focus on. Move to indicates the movement distance, set max speed indicates the speed, and set acceleration indicates the acceleration. The movement distance is specified by the number of steps. The motor makes one full rotation with 400 steps, meaning one step is 1/400th of a rotation. Specifically, one step, 1/400th rotation, moves the Q 0.005 millimeters theoretical value. I will now write the program and see how it actually moves. I instructed a movement distance of 400 steps. It moves exactly one full rotation. I instructed a movement distance of 400 to 800 steps. It moves exactly two full rotations. I instructed a speed change from 50 to 200. The rotation speed increases. I instructed a change in acceleration from 300 to 100. The acceleration becomes slower. That concludes the detailed explanation of the parts. Next, I will explain the structure of each part of the main unit. This is the overall view. It is divided into two main parts, the arm and the legs. The arm part is divided into 4 stages, from primary to quaternary. The leg part is also divided into 4 stages, from primary to quaternary. Each part is responsible for a specific function. The primary arm part handles the forward and backward movement of the Q. There is a large motor that provides the main power. It is very heavy, weighing 10 kg in total with 2 motors. There are also the bridge and grip parts. The secondary arm part handles the left and right movement of the Q. The secondary and primary arm parts are connected like this. The tertiary arm part handles the up and down movement of the Q. The tertiary and secondary arm parts are connected like this. The quaternary arm part is responsible for the height of the bridge part. It is positioned at the front of the entire arm, where it contacts the cloth. The primary leg part forms the basic frame of the legs. It has functions like easy movement with casters. The secondary leg part connects to the entire arm. It handles the adjustment of the entire arm's forward, backward, and vertical position. The tertiary leg part is responsible for preventing the entire leg from shaking and ensuring levelness. The quaternary leg part has the function of finely adjusting the position of the entire leg. This is the overall view. This is the actual cue point movement by motorized control. Left and right movement, with the front and rear motors in operation. Left and right movement, with the front motor in operation. Left and right movement, with the rear motor in operation. Up and down movement, with the front and rear motors in operation. Up and down movement, with the front motor in operation. Up and down movement, with the rear motor in operation. Checking the accuracy of the cue point movement. This concludes the explanation of the main unit. Although I skipped some details, it ended up being long. The 200 full ball endurance test is complete. This is how the conditions changed under the same conditions. Please continue to watch the actual shots, which are the main subject. Thin cut shot. They scatter quite a bit. The degree of wobble seems to vary as well. Follow shot with strong force. The thickness was adjusted to avoid a scratch. Follow shot with medium force. Follow shot with weak force. Draw shot. The highlight is the position where the cue ball stops. Full ball with side spin. The thickness was adjusted to avoid a scratch. Things are quite off. What could be the cause? There seems to be room for further verification. It looks like the cue is aiming automatically, but there is no such feature. I predetermined the cue's direction, and then made adjustments via the PC. A difficult shot. An extremely difficult combination shot. I tried shooting several times aiming for 9 consecutive successful shots, but each time, 1 or 2 balls missed. It seems difficult to achieve perfection. The reason is currently unknown. This concludes the actual shots, which were the main subject. Let's move on to the summary. Regarding the aiming accuracy and reproducibility, which are the premise of future verification videos. I don't think the results are perfect, but the performance seems to be acceptable for now. As possible reasons for the lack of perfection, there may be issues with the accuracy of this machine, or it could be due to other tools or conditions. I plan to verify and improve as needed. Another major issue is the lack of cue speed. Therefore, it is not possible to execute sufficient draw shots. The draw shot shown earlier is about the maximum. It is also not possible to adequately test brake shots. I would like to improve this in the future, but it would require changing the motor and making significant modifications to the main frame. And with that, this video comes to an end. At SETA channel, I use this verification machine, with the main concept of providing useful information for actual gameplay, and plan to post various verification videos. If you would like to support me, please subscribe to my channel and give it a thumbs up. Thank you for watching.